This is lesson 13 of our no-nonsense, no-frills A-level physics lesson series, the Whiteboard Physics series. And this lesson is all about the collision of electrons with atoms. Now, you may be wondering what this has got to do with quantum phenomena. We already met one quantum phenomenon before, the photoelectric effect. And what made that a quantum phenomenon was that light was caused by a stream of packets of electromagnetic radiation, packets of energy, which we called photons. And the electrons that were bound to the metal, the electrons that were within the metal, each electron would absorb a single photon, a single quanta of energy. And we had a look at that. Well, now we're moving on to collisions of electrons with atoms, not just with a metal surface, but with atoms themselves. And there are two things that can happen when electrons collide with atoms. Let's just make a note here. So two things can happen. And what are those two things? We could get ionization, or we could get excitation. Ionization or excitation. So let us start by looking at ionization. In order to start talking about ionization, we need to know what an ion is. And in chemistry at GCSE level, you may well have learned that an ion is just like an atom, but it's either gained or lost an electron. That's what we mean by this, by ions. So ionization is changing atoms into ions. And there's a few ways that can happen. And it can happen, charge transfer, electron transfer can happen through interactions between atoms in chemistry, but that's not what we're talking about here. So what we're interested in here, we are interested in ionization by bombardment. In ionization by bombardment. And in that case, we will always get positive ions, because what we'll do is knock electrons out of atoms. So always get positive, and we might use the shorthand for this, the plus VE for positive ions, by this method. So we're not denying the existence of negative ions, but we're just making positive ions by bombarding neutral atoms with electrons. But it doesn't always happen. There's a minimum energy that we are going to need. Now, this is where it gets a little bit complicated. We call it the ionization energy. So the ionization energy is the minimum energy needed. I'll make a note of this. Ionization energy is the minimum energy that we need to free an electron, from the atom in the ground state. So what do we mean by that? What do we mean by the ground state? Well, the ground state is an atom that has the least energy that the atom can have. Now, you'll remember from chemistry that we could lay out an atom. Let's do it on the right here. We could draw an atom as consisting of a positive nucleus with electrons orbiting it, just like this. And if this is a hydrogen atom, then we will have a single electron orbiting it. If it's a helium atom, we'll have two electrons orbiting it, and so on. But there are energy levels, what we could call shells, what we could call orbitals, that go beyond that. And you may have learnt in chemistry that you fill the shells starting with 2, then 8, and then, well, actually it's 18. But actually you start filling the 4th shell before you finish the 3rd shell for complicated reasons, which we're not going to get into right now. And so we've got all these energy levels. But what we're talking about at the moment is a bombarding electron coming in and then ricocheting off. And this bombarding electron is not to be confused with the bound electron. So this is the bombarding electron. Now, the bombarding electron has kinetic energy. And if it has enough kinetic energy, then it can knock an electron out of the atom, and thus it can ionize our atom. So we have an oops, that's still on eraser mode. Let's put it on a pen. Thus we have an electron that was in this particular state there. This electron comes off. It gets knocked out. And so we now have an ion, a positive ion. So the ionization energy is the minimum energy. If your atom happens to be in an excited state, which we'll talk about in a bit, then you can get ionization energies that are less than the ionization energy. But if the atom's in the ground state, then the energy that's required to cause ionization, the minimum energy, that's called the ionization energy. So an electron carrying a kinetic energy greater than the ionization energy can cause an atom in the ground state to ionize. I should probably write this down. Where shall I write it? Let's write it here. An electron, and let's call it a bombarding electron. Remember, we've got to make sure we clear the difference between them. A bombarding electron carrying kinetic energy greater than the ionization energy of the atom in the ground state can ionize the, that's not how you write the, can ionize the atom. Just like that. And there we are. That's the important bit of physics right there. Let's draw a little box around it. And so another way of looking at this is that a bombarding electron carrying kinetic energy less than the ionization energy of an atom, which is in the ground state, cannot ionize the atom. So the converse is true as well. Now we can measure the ionization energy of an atom. We can do that, and I'll make a little note here about measuring ionization energy. We can measure this ionization energy using a simple bit of apparatus. What it is we have a filament, usually tungsten because it's got a very high melting point. And what we do is we're going to connect to that filament a power supply so that current passes through that filament, causing it to increase in temperature. And because the filament gets hot enough, electrons are going to come off that surface of the filament by thermionic emission. Now, these electrons that come off the filament are probably just going to fall straight back to the filament again unless we accelerate them away from the filament. So we place at some position over here an anode. And that anode is going to be at a positive potential relative to the cathode. So how are we going to ensure that? We'll get another power supply is the basic gist of this. We're going to get another power supply. Now, we want to be able to change the potential difference across this gap. And one way to do that is just to use a variable power supply. And we use a diagonal arrow to indicate that. But that's a bit of a cop-out. So a better way of doing it is to use a potentiometer. So a potentiometer will look a little bit like this. We'll have a resistor, a fixed resistor, just like this. But then we'll have a bit where we tap off part of the potential difference, like this. Part of the potential, should I say. Let's just, I'm thinking out loud while I'm thinking I need to move some of this down. I haven't given myself enough room. So let's move this down a bit. There we go. And let's, yes, come on, click somewhere else. Thank you. And let's get the eraser out. I don't like editing these bits out because actually all of this gives you time to make your notes as well. So whilst it may not be the most interesting thing to watch, it's still useful. So we're going to do this. We're going to just place our connection just like that. And now what we can do is we can choose the potential difference by sliding the slider across on the potentiometer. Dead easy. Now we can measure the potential difference by slapping a voltmeter between here and here. And that will tell us the potential difference. And if there's no potential difference across that gap, the electrons are just going to leave the metal surface and probably fall back to it. But if there is a potential difference, we'll accelerate the electrons between the lower potential on the left and the higher potential on the right. So these electrons are going to be accelerated. And so we'll have other electrons here. They're all going to be accelerated from left to right because of that potential difference. Now, what we want to do is put all of this in a low pressure environment. So we take all of this and we put it in a vessel, in a container, where we reduce the pressure of the gas. It could be air, it could be helium, it could be hydrogen, doesn't matter. We're going to reduce the pressure of that gas right down. And in doing so, we don't want zero pressure, we want some pressure. If those electrons are able to gain enough energy moving across that potential difference, then their kinetic energy increases. If it increases to a point that it is above the ionization energy, we're going to get an electron colliding with one of the atoms of the gas inside that evacuated vessel, that low pressure vessel. It's not fully evacuated, knocking an electron out of one of those gas atoms, and now we've got two electrons. They're going to both accelerate, and if they gain enough kinetic energy, they're going to collide with other gas atoms and knock out more electrons. We'll have 4 electrons, then 8, then 16, and so on. And so this is a sort of a cascade effect, increasing the number of charge carriers that are moving across. So this is low pressure gas. That's important. Then what we can do is we can place an ammeter in this circuit. The ammeter has no resistance, so it's not going to affect anything in the circuit, but it's going to allow us to measure the current. Now, we're going to get a current. We're always going to get a current, even if there's an absolutely tiny potential difference between the anode and the cathode. Let's label them. Let's label this anode and cathode. But as we increase the potential difference between the anode and the cathode, eventually it'll be high enough that the kinetic energy of the electrons is high enough that when they bombard the atoms in the gas, in the low pressure gas, they cause more electrons to be freed. And so the current will suddenly go up. We'll see an increase, a noticeable step increase in current. And the potential difference where that happens, that is the potential difference that we can call the ionization potential difference. Right, so 1 second, cathode, and we're going to just make a note here that we get thermionic emission. If we haven't talked about that before, we will do later on. It's just where electrons are freed from a metal surface if they are given enough energy because of collisions with ions in that metal due to thermal vibrations. So there we go. What we'd expect the graph to look like? Well, let's have our potential difference on the x-axis, and let's have our current on the y-axis. We'd expect to see something like this. And where there is a sudden change, that sudden change there, that corresponds to ionization happening. Ionization happening. And how do you calculate the ionization energy then? Well, the ionization energy is the charge of the electron multiplied by that potential difference the electrons are being accelerated across. Remember, the definition of potential difference is the amount of work done per unit charge that's moving across between that potential difference. So the work done on that charge, well, the charge is the charge of the electron. And we can rearrange this equation to make that work done on the electrons the subject. And actually, this is why we have the unit electron volt. 1 electron volt of energy is gained, or let's say transferred, because it might be gained or lost depending on the polarity, is transferred when 1 electron moves across a potential difference of 1 volt. That is what we mean by 1 electron volt of energy. And this is where it comes from. It is a unit of energy because charge times potential difference is work that's being done. Just like that. So that's the essence of ionization. Now let's look at excitation. This one isn't going to quite go on as long because we're going to talk about excitation more in the next session. It's probably got an A in it. Excitation. So what's happening with excitation? Well, here we are concerned with electrons that are bombarding the atom, carrying that kinetic energy, delivering energy. I should point out, of course, that the bombarding electrons lose kinetic energy in this process. So the bombarding electron comes in, you can see this on the right, delivers some kinetic energy to the bound electron, making it unbound in ionization, and then the bombarding electron is ricocheted off with less kinetic energy because it's transferred some. Now in excitation, the amount of energy transferred is less than enough to get the electron to leave. So the atom becomes excited. We don't say that the electron becomes excited. We say the electron moves up in energy level, and we'll talk more about energy levels in the next session. But let's just do a quick sketch of it, because a picture tells 1,000 words. Here is my nucleus, and let's draw a few energy levels. Here's one with my happy electron in there, and here's another one. And we might have a bombarding electron coming in, colliding with an electron that's in that first shell, delivering its kinetic energy. Remember, that's the bombarding electron I'm using in green. And the electron that was bound moves up an energy level like that. Now, that means energy is stored in this atom because we have delivered energy from the bombarding electron to the atom. And in doing so, the bound electrons moved up an energy level. It's, we represent it as being further away from the nucleus, but it's not quite as straightforward as that. So we have transferred energy to the atom. The atom has that energy and it can release that energy later. And we can talk about the release of energy later. Now, the key thing that makes this a quantum phenomenon is that there are only certain excitation energies possible. So what is excitation energy? Excitation energy is the difference in the kinetic energy of the electron coming in and coming out, the bombarding electron coming in and coming out. It is the amount of energy that can be absorbed by the atom when it becomes excited. So make a note of that. Energy absorbed by atom. I mean, yes, it's by the atom, but of course it's by the electron in the atom. By the atom. It's like saying that you're not stuck in traffic when you're driving home. You are traffic. So energy absorbed by the atom when it becomes excited, which means it stores energy. Now, what makes this a quantum phenomenon is that there are only certain energies possible. There is a discrete set of excitation energies. possible. And it's different for different elements, it's different for different compounds. But I'll stop there because I think that's enough for us to go on. Usually excitation energies are in the order of electron volts, 1, 2, 3, 4, 5, 6, 7, and so on. And ionization energies tend to be sort of 10, 15, 20, not quite as high as 15 and 20, but they tend to be in those sorts of regions of electron volts. And that's the end of this lesson. Lesson 14 coming soon, all about energy levels, more detail about energy levels.